Hello guys, welcome to a part 1 summary of the Calc 21C or Calc 3 class. This video involves sequences, series, the convergence tests, all of them, power functions, radius of convergence, all that. This is right before the midterm one in our Calc 21C class. And I'm just going over this as a quick summary right before the final of like things to know and just quick, will I say, shortcuts or tricks and tips of how to do it. I'm going to be following this rubric that I made after going through all my notes and like the class curriculum and the stuff that's going to be tested on. So I'm going to jump straight into it, starting with number 1, knowing sequences are different from series. So series, or would I start with sequences? Sequences are just a set of numbers. So and so let's say 1, 2, 3. While series, on the other hand, are the sum of these numbers, and they usually have notations written like this. Say n equals to 1 or 0. And then they're both a of n, but usually on a test, series are written with this summation thing right here. Okay, next point. To calculate the convergence, like divergence in sequences, you just take the limit. So back to the same thing. In series, there are a lot of different convergence tests that I'm going to delve into later in the video. But for sequences, to check if the sequence converges, you just take the limit of as n approaches infinity of the sequence. And if it gives you a number, that means it converges to that number. Or if it gives you infinity, that means it diverges. For example, a sequence like ln of n plus 5 over the square root of n, to determine whether it converges or diverges, you just take the limit as n goes to infinity. And in this case, it's going to bring us to our third thing on the list here, where it says to solve the limits where it goes to 0, 0 or infinity. There are, well, what I say, strategically 2 key ways to do this is L'Hopital's, or try to see if you can implement an ln in this. So I'm going to go back to this function, and already has an ln, so wouldn't be smart to add another ln. So for something like this, where if it goes to infinity, it's going to give us infinity of infinity as the end. So what to do here is just L'Hopital's, which is derivative of the bottom over the top. So derivative of the top is just 1 over n plus 5 over derivative of the bottom is 1 over 2 to the square root of n, I believe. And then you can do the rest. Later on, you find out it equals to something like 0, but I'm just doing this as a time-saving strategy. Okay, next up, know the limit rules and know how to do this particular limit, because it's a very common limit to have. And I'm gonna do it real quick to show, but so it's 1 plus 1 over n to the n. Usually this limit is always equal to e to whatever number this is. So if this was plus 1, it would be e to the 1. If it was 1 minus 1 over n to the n, it will be e to the negative 1, because it's negative 1. If it was 1 plus 7 over n to the n, it will be e to the 7. And that's just the rule. You don't have to memorize this, because you can literally solve for this. It might be important to know how to solve for it, because you could be asked to like evaluate this limit without using a theorem. This is a theorem, so you can't just say, oh, it's going to be e to the something. And to do this, you use a combination of what I just talked about, how if the limit, so you're trying to evaluate the limit as this goes to infinity, instead of just plugging it in, you use ln. It's a trick here where you take both sides, ln, and then at the end you do e to the limit. But for now, ln, and why we're using ln is so we can bring this n to the front right here. So it's going to become n times ln of 1 plus 1 over n. And look, the n, what I say, to the n power is gone, and it's here now, and that makes it a lot easier to evaluate. So now from this point, we can convert it to this ln of 1 plus 1 over n over 1 over n. Because remember, basically n times ln of n is the same thing as ln of n divided by 1 over n, because it's the same thing. I'm just going to keep going for time's sake. And now you do L'Hopital's now at this point, and the derivative of the top is 1 over 1 plus 1 over n over, times, chain roots. So the derivative of this inside, 1 over n, the derivative of this inside is negative n, negative n squared, negative 1 over n squared, and negative 1 over n squared. So they both cancel out, so just this cancels out, and you're left with 1 over 1 plus 1 over n as limit goes to infinity, and then this goes to 0. So you're just left with 1. And then remember, it's e to the limit. It's ln of e, the limit, so you have to take both sides, e to both sides to get rid of the ln. And then your answer is this, basically e to the 1, which is what I said it will be. And it's just important to know how to manipulate limits when you can't find them. Okay, next up is, now we're doing series. Series, like I said, series are different from sequences, and you're gonna have to know how to check for different kinds of convergence and divergence in different kind of series with multiple different tests. So we're gonna hop straight into the test here, and the first test to always do is, by the way, these tests, how to do these different tests are on my YouTube channel. You can look at other videos to see how to, or brief description of how to do them. So, because I'm gonna be speed running it here. So right here, we're gonna start with the end term test. So let's say you're given a function, literally any single, not function, so used to saying function, series, random series, like 1 over n squared, something like this. The most important thing to do for this, before you like if you're advanced in calculus, you know that this is going to converge. But the first thing to do, or the safest thing to do, is do a limit as n goes to infinity in your head before, because that's the end term test. Because if this equals anything other than 0, then you know that the series diverges straight away, and then you don't have to do any test, and then you stop there and you get your answer. And in my last midterm, I had a problem where I could have done the end term test, but I decided to do another test. And although I did that test right and determined that it diverges anyways, I still got it wrong, because I guess professors would rather you do end term if you can do it. So it's always important to do it. And the reasoning behind this to remember is, if the series, so as if for n, as you take the limit as n goes to infinity, the series has to equal to 0 if it's decreasing. So, and the series has to be decreasing to converge. Like if the series, so think about it as a function. If the function is like increasing, it's not really going to converge. It's going to keep going up and up and up. But then, let's say a function is decreasing towards the x-axis and going smaller and smaller, so it's going to get closer, closer, it'll probably eventually converge. So the idea is that it's negative and decreasing, so more likely to converge. Okay, next up is a geometric series. And geometric series are just any series that looks something like this, where you have a bracket like 1/2 to the n. And to check for convergence, this is also another easy series. You just look at whatever is inside this. So it doesn't matter if there's a, so let's say this is like 5 inside. This is a constant, just like in functions. When you're doing like derivatives and integrals, you can just move this to the outside. It doesn't really affect what's inside. So what we're checking is what is being raised to the n power, and that's called the r. And if r, the absolute value of r, it can be negative, it doesn't matter, is less than 1, so it can't equal to 1. If it's equal to 1, then it's convergent. So if it's less than 1, it's divergent. If it's less than 1, it's convergent. And if r is greater than or equal to 1, then it's divergent. And also, geometric series or geometric test is one of the cool ones where you can find the sums. So if you ask for the sum, it's a geometric series. It's just a over 1 minus r. A being the first, I think a is the first term. Yeah, so in this case, the first term, let's say we start at n equal to 1. The first term would be 1/2 to the 1 power, is 1/2 times 5. The first term would be 5 over 2 over 1 minus the r, which is 1/2. And then whatever you get is the sum. Okay, next up. Oh, it's also still on geometric series. It's important to know how to manipulate functions to give you the proper form. So still on the basis of geometric series. So let's say you have a function. I keep saying function, a series. Like I'll use like the same series where it's let me try to come up with a different series. Let's say this series is 5n minus 1 over 2 to the n, something like this. And you look at this, you're like, damn, this is confusing. Oh my god, it's intimidating, all that. Just know that if both of the numerator and denominator both have n's, it doesn't matter if it's like minus 1 or if it's something like over 2. Man, maybe over 2 wouldn't really work. No, that's just, most likely you're just going to see something where it's minus 1 like this. It's also important to know, especially in series, that a lot of this trick I'm going to show you is going to be important in other, other parts of the series as well, especially like ratio test later on, where you can, if you know, mathematic rules, you can multiply this 5 into n and into 1. So the exponents of, let's say, if 2 is raised to 1 plus 2 power, this is basically 2 times 2 to the 2 power. If that makes sense, you can apply the same thing here, where this is basically 5 to the n times 5 to the negative 1 power, which is just 1 over 5. So you can manipulate this whole function to become 1 over 5 times 5n over 2n. And then, you combine these n's together and becomes 1 over 5 times 5 over 2n. And now you have a geometric series with the r greater than 1, which diverges. Okay, next up, telescopic series. So telescopic series is important, where if you see something like it said here, like ln of n plus 1 over n, I think that's, wait, I wrote it wrong. It would be ln of n plus 1, wait, where it looks something like this, ln of n plus 1 over n, something similar to this. But before I get to that, I'm going to talk about what telescopic series is. So a simple telescopic series would be something like n minus 1 times n. And then why this is telescopic is because, let's say you plug in 1, 2, let's plug in 1, 2, 3. So if you plug in 1 for n, it will be 1 minus 1. Actually, since it's 1 minus 1, let's do 2, 3, 4, because the first term is just going to be 0. 2, 2, 3, 4. 2 minus 1 is, am I doing this right? Yeah, 2 minus 1 would be 1 times 2. Wait, I'm not doing this right. This is not a good function. Okay, instead of n, I'll do n plus, so it's easier. Yeah, and also the mistake I made was this is minus, not times, because there has to be like, a subtraction factor going on here. So it'll be still plugging the same numbers. 2 plus 1 is 3. 3 and then minus 2, so it'll be 3 minus 2. That's for 2. And then for 3, 3 plus 1 is 4 minus 3. And then 4 plugging in, 4 plus 1 is 5 minus 4. And the thing to notice here is that these numbers cancel out. So like you see it, 3 cancels out, 2 doesn't cancel out yet, 4 cancels out, and then you're left with like negative 2 and 5. But then if you keep going here, let's say plug in the nth term. So nth term is like going to infinity. So you keep going 2, 3, 4, 4, 4, whatever, and then whatever number just becomes n. And let's say plug in the nth term, but before we do that, the number before is let's say the number before n is still 4. Or would I say, wait, yeah, plug in the n term right here. We're still, hold up, n plus 1. And then it'll be, the other number will be minus, it will be 5, because let's pretend 5 is the number before n. All I'm trying to do, I'm trying to cancel the 5 so you can see what telescopic series looks like, because it keeps going and on and on. So the numbers you're supposed to be left with is -2, and then -2 plus n plus 1. And then you like do the limit as n goes to infinity with whatever you're left with. And this scenario, you get infinity, so it diverges. But if this is like 2 minus 1 over n plus 1, which is what usually or what can happen in telescopic series, where it goes to 0, and then it just converges to the initial value here. Anyways, I just wanted to show another way of telescopic series can look, which is like this, where this might look confusing and you would not know what to do, but just use log rules, where the log of something on the top over something at the bottom is just the same as ln of n plus 1 minus ln of n. And as you can see, it looks similar to that one, so it becomes telescopic. By the way, this does diverge, I checked. Next up is integral test. It's one of those looked over ones, because it's not that difficult, but then you just have to kind of keep it in the back of your head and try to spot it and remember. So integral test is, let's say you have a series. I'm going to use a famous series here. So 1 over n, this is a harmonic series and it diverges. It's a common series that people know that diverges. But for something like this, I'm just doing it because it's something easy to integrate. I can do quick in this video. But usually if you see any sort of series that looks like something you can integrate or something you can u sub, so let's say something like x over ln, not ln, but I say like x over x plus 1, or not the opposite actually, like something like x squared. Actually, x would be on the bottom, right? If you integrate it to u sub, yeah, x would be at the bottom. So like something like x squared plus 1 over x. If you want to integrate, if you want to do the I mean not x. Usually series would be given with n, but one thing I forgot to say earlier was that n can become x and you can integrate it. So let's say something like, if you're given something like this, you can just integrate it where you do u sub. Just anything that looks like you can integrate it. Usually the functions would look like, it would usually have ln's. So I'm going to give an example of a hard looking one. So something like this, where it's 1 over n ln to the n squared. So something like this is going to look really hard to know what series test to use, but you know that you can integrate this ln of x du dx. If you take it as u equals to ln of x du dx equals to 1 over x, and then it flips, and then this becomes, remember you can change n to x, so this becomes ln of u squared, and then du x du, and the x cancels out and you're left with 1 over u squared, which you can integrate from. Usually this would be like, it will start at n equals to 1 or n equals to 0 and goes to infinity, and then that's how you integrate it. You integrate it from 1 to infinity, 1 over u squared, whatever the integral is. And then if it gives you a number, then it converges to that number. If it gives you like infinity, then it goes to infinity and it diverges. And that's the integral test basically. I'm going to do this one real quick because it's easy to do, to show you. So the integral of 1 over x is x to the 1. That's just, that's just ln. Yeah, that's just ln of x. And then remember, integrate it from 1 to infinity. So plug in infinity, ln of infinity minus plug in 1, ln of 1. Doesn't really matter because ln of infinity goes to infinity. and it diverges. Okay, next up, make sure to prove, yes, this is very important, decreasing continuous positive. So for integral tests, there are three things you have to prove for you to be able to use it. You have to prove that it's decreasing. You have to prove it's continuous. And the last one was positive. So for these, on our test specifically, I don't know about other institutions, but you don't specifically have to prove that it's decreasing. Like that'll take a lot of time. So you can just write these three traits out, which it has to have, and check it and say it is, because usually it will be. Like if you can integrate it, then it usually passes these requirements. Next up, P series, pretty common. Like I showed over here, so like something like 1 over n, whatever this is raised to. So right now this is raised to 1 power. In P series, it has to be greater than 1. It can't be 1. Greater than 1 to converge. And if it's less than or equal to 1, then it diverges. So something like 1 over n to the 1.5 would converge because it's greater than 1. 1 over n to the 10 would converge. Something like 1 over n to the 0.5 would diverge. It's pretty easy. It's just used for other comparison tests, usually P series. Like you're not going to get a question this easy on a test. And straight into it, using P series, you go into the direct comparison test. So direct comparison test, it's comparing if a series converges or not by comparing it to another series. So for example, like what I say, 1, or if I'm going to do a really easy, 1 over n squared plus 1. Does this diverge or converge? The way to find out is you compare it to something that you know converges, so 1 over n squared. It looks really similar, right? But then the trick in using direct comparison is that if you're trying to prove it converges, you have to compare it with something bigger. And if you're trying to prove it diverges, you have to compare it with something smaller. So back to here, how to know which series is smaller? You just look at the differences in the denominator. So this one has a bigger denominator, and the bigger the denominator is, the smaller the number is as a whole. For example, 1/2 versus 1 over 1. You know half is smaller than one whole number because the denominator is bigger. So that means it's going to be smaller. So right here, you're adding 1 to whatever the series is, but here you're not adding 1. So we know this number is smaller, and we know this converges because P series converges. So that means this has to converge as well. And the theory behind that, to help you remember this better, like I drew early in the graph. So let's pretend this is 1 over n squared. If it converges, you know, it's decreasing, it looks something like this, and it converges to a certain point. If we want to prove the other one converges, we can't like our desired function that we're looking for can't be bigger than this, because then otherwise it doesn't really prove anything. But then the idea behind it is if this function that we're looking for is smaller than this one and this one converges, then this one has to converge as well. That's the idea. And then it's the opposite for divergence. For divergence, we're using the direct comparison test. So let's say this is the function that we know that diverges, you know, goes like this. It doesn't diverge to anywhere. The function that we're trying to, the series that we're trying to prove diverges has to be not bigger. It has to be bigger than this one, because then if it's smaller, we never know if it like converges eventually because it's smaller. But then if we know that it's bigger, that means it has to diverge as well because the smaller one is divergent. That's just the idea behind it. Anyways, now move on to the sister of direct comparison. It's limit comparison. It's basically the same thing, but I think limit comparison is more easier because direct comparison, you have to find you have to find one that's smaller or one that's bigger. But limit comparison, you can just compare similar looking series. So like something like this, you just set it n equals to limit as it goes to infinity. And the function, so usually the function that we have and what we're looking for is called a of n, and what we're comparing it with is called b of n. So for limit comparison test, it's going to be a of n over b of n. So this one's going to be 1 over n squared plus 1 over 1 over n squared. And we can just write this as when you do 1 over n squared plus 1 times, n squared over 1. Then it becomes n squared over n squared plus 1. And when you take the limit as n goes to infinity, the leading coefficient, this goes to 1. And the rule said here, limit comparison, if it's greater than 0, then they both either converge or both diverge, and 1 is greater than 0. So that means whatever, these two follow the same rules, and we know this one converges, so that means this one has to diverge as well. Next up, absolute convergence test. So this one's just, it's more of a reading thing. So like I could just read it. If the absolute value of whatever series you're looking for is convergent, then it's absolutely convergent. If it's divergent, if the absolute value is divergent, but the main series is convergent, then it's conditionally convergent. And if it's divergent, then the whole thing, if the non-absolute value is divergent, then the whole thing diverges. And I'm going to show an example with the alternating series test, and also do the alternating series test as well to show it. I found a good function for proving absolute convergent. So to prove absolute convergence, well, the best route, or would I say the best strategy, is first of all find the convergent if the absolute value converges, because if it does converge, then you're done with the whole problem, and you can just say it converges absolutely. But then if it doesn't converge, then you move on to this whole thing. So this is known as a of n, and then the absolute value of this would be, just take out the whatever is, this is n by the way, whatever is making it alternate, which is the -1 to the n in front of it, because that, that's the alternating thing. It makes it alternate because it goes -1, then 1, then -1, then 1. And if you take that out, take the absolute value, takes that out, and you're just left with this part of it. So you're just left with n plus 1 minus n. And then if this absolute value is divergent, then you find if this whole thing converges with the alternating. And in this problem, I'm going to do that using the alternating series test, AST test. So the first one, we're going to do check the convergence of the absolute value of the series. And this is a telescoping series, and one thing about telescoping series is that, one thing I know is like this series up here, actually I think it's the exact same series but with a squared instead, but the idea remains. Usually when it's when it's not 1 over, if it was 1 over something, it's gonna converge. And the trick is that, this is a trick, I'm not sure it works all the time, this is not mathematical proof by the way, is if you know it's alternating series, you already know the insides are going to cancel out, and you're going to be left with the starting number, which is what you're going to have to take the limit of n as it goes to infinity of the starting number. So let's say we start with 1. The starting number is going to be 1 plus 1. It's going to be the square of 2. And then you're going to end with, like here, we ended with n plus 1. So you're either going to end with n plus 1 or n. And it doesn't really matter what you end with, either n plus 1 or just n, because when you take the limit to infinity, you're going to get infinity if it's not 1 over n. So the whole point is the absolute value diverges. So that means it can't be absolutely convergent. This series can't be absolutely convergent. And now we do the, like I said, the alternating series test for the whole thing now with this. And there are 3 conditions that proves that a series is an alternating series is convergent. So when you see it has an alternator right here, this could also be like cosine of n, because cosine of n alternates. So like if it has an alternating device in front of the series, then you just do the alternating series test. And that's to prove that, first of all, it proves that the function is decreasing. What did I say? Also prove that the limit of the function goes to 0 and the function is positive. So two of the traits are the same as the integral test. And for this particular function, I'm pretty sure it passes the alternating series test, and we can test it by so obviously it's positive, and the limit, you know, one thing about this that you can do for the alternating series test is, and I checked this function just right now, it does pass the alternating series test, I was right, but then to see it better, you have to put this in a conjugate form, which just means, you know, n plus 1 minus n. You multiply this function by the positive, so n plus 1 plus n over n plus 1 plus n. And after you do that, you get 1 over the whole numerator cancels out, because this, when you multiply each other, it just cancels out and you're left with 1 over the denominator. So now you can see that it's clearly obviously decreasing, and the limit goes to 0, so it passes the alternating series test when you include the alternator basically. So it's conditionally convergent. Okay, moving on. Where are we again? Okay, we're done with that, and now we do ratio test. Ratio test is one of my, not my favorites, but one of my most used tests. It's important for other concepts as well. We move on to radius of convergence and whatnot. But ratio test is basically taking a to the n plus 1 over the original function. So you take the original function, add 1 to it, and divide it by the original function, and you're doing this, the absolute value, by the way, with the limit as n goes to infinity, and whatever you get right here is sorry about that, when this is equal to p, and if p is less than 1, then it converges. And it converges absolutely because of the square root, so you can technically say it converges absolutely. It's greater than 1, it diverges, but then when it's 1, it is inconclusive, and you probably have to do another test. And let me find a good function you can do with ratio test. This is a nice, easy function. Well, not nice and easy, but you can do a ratio test. And the trick with ratio tests or functions, whenever you see a to the n power, I think I say it right here as well. Use when given factors or x to the n power. Because of the trick you can do with ratio tests, whenever you see a factor to the n power, it's smart to use especially factorials, the root test. So what does a to the n plus 1 look like? It's just whatever or wherever n is. Sorry about that, my PC's running low. Whatever n is, add 1 to it. So over here, you have negative 100, and then you have n. Just add 1 to the n. And then with the factorial, you have n factorial, just add 1 to the n. And then cover it out, then put the parentheses as well. And this is a to the n over 1. I'm going to come down here and continue. So you just put whatever you got. So negative 100 to the n plus 1 over n plus 1 all over the original function, negative 100 to the n over n factorial. And I'll rewrite it to make it easier to look at. To the n plus 1 over. This is just the same thing. I'm just putting the function. Putting the division in an easier way. So flip this n factorial over negative 100 to the n. And the trick with this is, remember how I told you math, you can multiply this into this and this into that, and it's just negative 100 to both powers multiplied by each other. So it becomes negative 100 to the n power times negative 100 to the 1, which is just negative 100, and just negative 100 over n factorial. The trick here is, so a factorial of a number, like 5 factorial is 5 factorial equals to 5 factorial times 4 factorial times 3 factorial, and it goes on. So the trick here is that it's 5 and then 5 minus 1 factorial, then 5, still 5 minus 2 factorial. You use the same trick here for n minus 1 factorial. So n minus 1 factorial is just n minus 1, like 5 is here. I mean n plus 1 times n factorial times n minus 1. So it keeps going minus 1 factorials, but we can just stop at n because we see there's an n here. So like we see over here with the negative 100, there's a negative 100 n that's ready to get canceled. And just like here, we see an n that's ready to get, n factorial that's ready to get canceled. So you're left with negative 100 over n plus 1. That's the trick. So to cancel the factorials and cancel the roots. So now you can easily take this limit, so n goes to infinity, and then you have a number, negative 100 over something with n, which goes to 0, which is less than 1, so converges absolutely. Okay, next up is the root test, which is, it's like the ratio test, but it's used less. It's just similar thing. I think absolute value as well of the root of whatever a sub n is, and it has the same, this is called rho, p-value, but it's called rho, but I call it p because it looks like p. I'm gonna try to find another good function for ratio test. Okay, this is a decent function for root test, and you might think, I can't take the root, the n root of the top one, because you have to, n root of the top and bottom. I can take the n root of the bottom one, but hey, I can take the n root of the top one. Yeah, you can. N root is just whatever number you have. So like if you have 5, it's just the nth root of 5 is just 5 to the 1 over n, just like the square root of 5. So square root of 5 is just 5 to the 1/2 power. So it's the same thing. So for something like this one, you just becomes the absolute value of, so the negative gets rid of, you get rid of the negative since the absolute value, and it's just n to the 1 over n over ln of n to the n. Obviously the n goes away because you're taking the nth root, and then you're left with this, and then you take the limit as n approaches infinity of this, and then when n approaches infinity, 1 over n goes to 0, so the top part goes to 0, which makes the whole numerator go to 1, because anything to the 0 power is 1 over, wait, we ran into a problem here. We can't just, because now we have ln of n, and to go infinity is just going to be 1 over infinity. Oh wait, that's not a problem. That's just 0, right? That's just 0. I was tripping. That's just 0. So the whole thing goes to 0, less than 1, converges absolutely, just like the other one. And that's actually it for the series test. Wow, we did the series test that quick. All of these. Not bad. Okay. Now we only have a couple things left, but these couple things do take a while. I'm gonna go straight into convergence of radius of convergence, and radius of convergence is just, so you have a series that look like this, like usually, so as you can tell, this is a geometric series with this as the r, x over 2 10 to the n. This is geometric series, and this is r. Then this doesn't look normal because you have an x here. Oh, you're asking, how do I have an x and an n? It's 2 variables. The x is the only variable, and you're looking for what can the x be for this to still be convergent. And if you think of this logically, you can see that for the inside to be convergent, remember we said r, the absolute value actually of r has to be less than 1. It can't be 1. So what can x be? So like, let's start putting pretend numbers. So let's say x is like, let's say x is 10. If x is 10, it'll be 10 minus 2 over 10. It'll be, what's 10 minus 2? 8 over 10. Hey, this works. 10's in it because 8 over 10 is less than 1. If x is like 15 over 2, it doesn't work because it's greater than 1. It doesn't work. This one works though. If x is like, let's say x is 2, 2 minus 2. Okay, that works because it's less than 1. If x is like negative 4, negative 4 minus 2 over 10. Negative 4 minus 2 is negative 6 over 10. That also works because the absolute value of this is also less than 1. If x is something like negative 15 though, it'll be over 10. It will be negative 17 over 10, whose absolute value is greater than 1. So it doesn't work. So you get what I'm trying to say? We're not doing this, we just be guessing numbers. There's a systematic way of solving this. And let's just say for this is easy because it's geometric. We just know it has to be less than or equal to 1. So that means there's a number, so between negative 1. So it's greater than negative 1, but it's less than 1. And within that, we have our numerator here, which is the one with the x that determines it, so x minus 2. So what numbers can x be for it to be between over 10, by the way? The whole thing is going to go in it. What numbers can x be for it, this basically to stand? What to do is multiply the 10 to both sides. It's like an equation where you have two sides instead. So whatever you do to the left, you have to do to the right. So you multiply 10 to both sides. So negative 10 to the x minus 2 less than negative 10. I mean positive 10. This side's positive. And now you have to get rid of the 2. And how you do it, you just add it, just like the equation. So negative 12 less than or equals to x and 12. So that means x is between 12, negative 12, and 12. But we don't know, so we just plug those numbers in to test it. So we don't know if the notation is going to be like that, or if it's going to be like this, or 1 bracket, 1 square. So we just plug it in. Negative 12 minus 12 is negative 14 over 10. That's not going to work. Put in 12 though. 12 also not going to work. So that means it's going to look something like this. Oh, and I messed this up. This isn't negative 12. It's negative 8. Because negative 10 plus 2 is negative 8, not negative 12. I was going to say. It still stands though. You still, this is still the answer. Because negative 8 gives you 1, and that doesn't work. So it's not including 8, but it's the interval between negative 8 to 12. And then there's another way of doing radius of convergence with the ratio test instead. I'm going to show that. So for this, instead, when you look at this function, this series, you can tell that it's obviously not a geometric series. And usually for, if they ask radius of convergence, usually it's either going to be geometric or ratio test. Or even root test, but usually it's geometric or ratio. So let's say they ask what's the radius of convergence for this, when it, how to determine it has the x. So that's what we're going to be looking for. So since this has to the n to the nth power, usually we use ratio test for that, since we can't use geometric, since this bottom one doesn't have n to the nth power as well. So we do a ratio rule, which is a to the n plus 1 over a to the n, and remember absolute value, so we just get rid of this whole thing over here. So it becomes x to the n plus 1 over n plus 1 times, this is divided by the way, but I'm flipping it, times the original function to make it quicker, x to the n. And remember the trick again, the x to the n, remember this is absolute value too, by the way, I forgot to mention that. Since you're taking the absolute value, the x becomes absolute value. And then it comes, when multiply those out, comes absolute value of x to the n times just the absolute value over n plus 1 times n alone over x to the absolute value of n. And luckily something cancels here, but then we're left with the rest of this, and we just, put the limit as n approaches infinity, and then we're left with the absolute value of x times n over n plus 1. As you can see, these all go away because they all equal to 1. N over n is just 1. So we're left with just absolute value of x. And now, since we have an answer here, remember in the previous ratio test we did, whatever answer we got, the p, so this is equal to p, the absolute value of x, whatever answer we got, if it's less than 1, it means it converges. Greater than 1, it means it diverges, but it can't equal to 1. So to determine the radius of convergence, it's just whatever converges. So -1 usually converges. That means since p, when p is less than 1, not negative, less than 1, it converges. That means this p, which is p, has to be less than 1 to converge. So whatever radius, whatever numbers you put in here that's less than 1 converges. And it becomes something similar to this one where absolute value of x has to be less than 1. So that means it can be like -0.5, but the absolute value of 0.5 is still less than 1. So we write it like this. So it's the similar thing where it's -1 greater than x, less than x, less than 1. And this is the radius, I'd say. But then we have to test if it's this or this type of bracket. So if it includes -1 and 1, now we do that is we just plug it back into the original equation. And if we put -1 in here, I think -1 to the n. So it cancels out this alternator. So it's just 1 over n, and that diverges. So -1 is not included. But if you put 1, I'm pretty sure this converges. You just have to, you can check on your own. 1 over this, since it's alternating, and this passes the what was that? The AST, the alternating series test. So it's decreasing. The limit as n goes to infinity equals to 0, and it's positive. So it passes this series, passes the alternating line test. So that means the radius of convergence is going to look something like this, where the -1 isn't included. Like this, but the 1 is included. That's the radius of convergence. So next up, series has an x in it. Oh, that's the radius of convergence. Usually used with geometric tests, like I said, ratio test. And one thing is, if the limit, so if I'm done, so let's say I did this, and I got, where is it? Instead of absolute value of x, let's say this gave me 0 instead. Since I can't solve for anything, I can't do this. The radius is just -infinity to infinity. It's all real numbers. Next up, Taylor and Maclaurin series. These are more difficult per se, so I'm just gonna go to my notes and show that at the end to finish up the video. I'm gonna go to Taylor series. So Taylor series, there's a formula, this formula right here, where you just find the derivative of the function and plug it into the formula. Maclaurin is what we're going to be focusing on in this class because that's what the last midterm had, and just what we did more in class. Just find the derivative of the function and follow the formula right here. E to the x, find the derivative of e to the x at 0, and then you put it into the function times x squared over 2 factorial. There's stuff like that. And then more of that. When they ask for second order, it means stop when it's x squared. Third order means stop when it's x to the cube right here. Fourth order would mean x to the fourth, and so on and so forth. And then the last topic, which was right here, term by term differentiation and integration. It's about right here. So let's say this term, if you do, it's just basically derivatives and integral. When you derive it, it becomes, when you do the derivative of this, it becomes that 3x over that, which becomes that. Just derive it individually, derive it term by term, and the equation also changes as well. It's pretty cool. Let me try to look for a cool example. Now there's one in here somewhere. So like, yeah, like this. So let's say you have, wait, not this. Am I tripping? I can't find it anymore. Oh yeah, that. Let's say you have the equation of the series, power series. This is it. And they ask you to integrate it. You just integrate the part with the x right here, which is a variable. You know, x to the 4k. How to integrate? You just add 1 and divide by what you added 1 to, which is that. And that's how you integrate it. And then you add it, you know, to the rest of the other stuff. And then something like this, when they ask you, you know, this is the original function was cosine of x, and now they ask you cosine of x squared instead. You just replace x with x squared. So this used to be x squared, x to the 2k. Just replace it with x squared, it becomes x to the 4k right here. That's basically it. But anyways, thanks for watching. Hope you do good in finals, midterms, all of the above. And hope this helped. Hope it helped for me as well, and I do good as well for myself. Bye.